Good morning. Now, today we're going to talk about different types of fuel cells, and I won't go through all of them, but what I will explain is that there are different types, and every fuel cell has a use. So this is not a descriptive example of fuel cells for the purpose of competitiveness. It is basically information as to what fuel cell types there are. But first, before we go on that, an interesting thing to report, and that is if you remember in one of my earlier podcasts, I talked about data centers and their effect on consumer costs. And this is very well shown in the state of Georgia, where the cooperatives, in other words, the ESCOs owned by their subscribers, are competing with Georgia Power, which is a state-operated, investor-owned company. There is a dispute between Oglethorpe, which is the main supplier to a cooperative in Atlanta, Georgia, and Georgia Power over the costs of a nuclear power station. And the interesting thing is that Oglethorpe is pushing for lower pricing, lower tariffs to their customers than Georgia Power. Georgia Power is trying to make them charge the same amount so that they can remain competitive. So that gives you an example of one of the things that happens between having a privately owned utility or an investor-owned utility and a subscriber-owned utility, Oglethorpe being the subscriber-owned utility. But one of the pressures is that they are building very large data centers in the state of Georgia, which are supplied by Georgia Power. Big surprise there. And so the data companies can absorb the price difference, while of course the consumers can't. What difference does this make? $9 a month in additional charges for those who are not a data center, those are ordinary consumers. But the reality is it's probably more than that. So that's just the headline figure. Now, how does this affect Sefton? Well, if data centers are going to be built in the UK, then that will obviously start increasing the demand for electricity. And if there's an increased demand for electricity, there's increased pricing. Now, the idea being that if you have a subscriber-based system, then the subscribers determine what the price of the electricity is and benefit from any profits thereof. In other words, the money goes back into the community. So it's well worth considering this when you think about what happens in the future in electricity. Now, enough of that, going on to fuel cells. There are two distinct different types of fuel cells. There's high temperature fuel cells and there are low temperature fuel cells. The benefit of high temperature fuel cells is that they self-reform. In other words, you can put methane or you can put natural gas into them and they'll reform them into hydrogen. The disadvantage of that is, of course, it's no different from putting it into a thermal electricity plant. Well, there is a slight difference, but in principle, you'll still be creating CO2 and other gases as well. So the only real advantage of high temperature is efficiency and the internal reformation of various feedstocks. Now, no one has actually tried yet to put in ketones or something like that into a high temperature fuel cell because there are only really very few high temperature fuel cells available. And even then, they tend to run at a higher temperature than necessary. For example, phosphate fuel cells, which can run at 250 degrees centigrade, would have to be run at considerably more, maybe up to 800 degrees centigrade in order to be able to self-reform. The same applies to molten carbonate fuel cells, and I'll go into what they are in a few minutes. And the same also applies, of course, to solid oxide fuel cells, although solid oxide fuel cells do run at a higher temperature to begin with. So the three high temperature fuel cells are phosphoric acid fuel cells, if you can call them that, molten carbonate fuel cells, and solid oxide fuel cells. So what's the difference? The difference is one of whether or not it's acid or it's base or it's neither. Now, the phosphoric acid fuel cell is, as it sounds, it's an acid. And the molten carbonate fuel cell is a carbonate, so it's a base. And the solid oxide fuel cell is neither, although it does actually use both acid and alkaline. So let's start with the phosacid fuel cell. The phosacid fuel cell was the most commonly made fuel cell in the 1990s and 1980s. It was a very good system. It was basically engineering, and it was very clever. The engineering was absolutely superb. I can't knock it on that. What I can do is say this: it's phosphoric acid, which means that you have corrosion problems, one. And then the second thing is the reactant time is slower than alkaline. So as a consequence, what happens is you get less bang for your buck in many ways, and you have a lower efficiency. You also have the problem of corrosion and lifetime. So phosacid was good for about a year, about 40,000 to 80,000 hours would be fine for a phosacid system before it would have to be rebuilt. And that was a costly, a very costly venture. The efficiency wasn't that terrific. It was between 50 and 60%, around that kind of figure. So it wasn't brilliant, but it was okay. It worked very well, but it had to be very carefully maintained and very carefully tended to. So it wasn't a build and forget system by any stretch of the imagination. The people who built most of them were a company in Connecticut called United Technologies, who were a pretty good company, but they were subsidized heavily by the state of Connecticut, who poured billions into the company. What they got out of it is questionable, because I'm not sure that the electricity prices reflected the actual real cost of the technology. The other countries that produced phosacid were Korea and Japan, who took to them like a duck to water and built many, many hundreds of them under license to UT. So they were, to a certain extent, hegemonous. Would I recommend using a phosacid? No, not really. It's old technology. It hasn't moved very far. The material costs are relatively high. The actual cost of the fuel cell is between $2,000 and $3,000, maybe even more dollars per kilowatt. So it's an expensive piece of kit, difficult to maintain, and with a short lifetime. The second high temperature fuel cell is the molten carbonate fuel cell. Now, I actually like molten carbonate fuel cells. Their real problem is that they haven't advanced with the advance in technology. They built mostly of nickel, and they're very heavy. So there's a lot of nickel in them, so that becomes quite expensive, albeit they have high efficiency, 60 to 70%, which is not bad. They operate at best at high temperature, 600 to 800 degrees centigrade. By the way, the phosacid fuel cell will work as low as 250 degrees centigrade. So that's really the difference between the two. One is higher temperature than the other. The problem with the molten carbonate fuel cell is you have to keep the electrolyte, which is molten carbonate, liquid, and that means you have to keep the fuel cell fired up at all time. You can't actually let it drop below the melt temperature of the molten carbonate. In terms of lifetime, it's very good, actually. Lifetime can be 10 years without a huge amount of maintenance. So it's quite a good fuel cell from that point of view. It's engineered, which means that is all engineering. Industrial processes really don't enter into phosphate fuel cells. They are actually made with guys with tools. This may be a good thing economically. The actual cost is relatively low. You can probably make a molten carbonate fuel cell between $800 and $1,500 per kilowatt. So that's not too bad. In terms of mobility, it's not a very mobile system. First of all, you've got molten carbon sloshing around, which is a bit dodgy. But the second thing is this: is that if you actually have to turn it off, it becomes solid again, and then your startup time is quite significant if you can start it at all, if it hasn't actually broken down. So the advantages are that if you're going to put it in a stationary situation, it's a good fuel cell. It works well. It has a long lifetime. It has relatively high efficiency. So that's a good point. And it can be large. So you could have a meter square electrode in a molten carbonate fuel cell without much difficulty. Here's the interesting thing. The most advanced molten carbonate fuel cells were developed in Holland. And they were not in Holland, rather in the Netherlands. I always say Holland, but Holland is only a part of the Netherlands, in the Netherlands. And it was highly subsidized. The work was highly subsidized by the Netherlands government, which is not unusual in the Netherlands. The problem is that they stopped funding it, and they stopped funding it because they had a civil servant who went, look, this is all nickel, and they neglected to take a look at the fact that a lot of it was also steel. And they said, oh, look, it's all nickel, it's too expensive, we'll never get the price down, and stopped funding the company that was making it, whose name I've forgotten. But anyway, they stopped funding the company, in which case it went bust, and it was very, very clever. If they'd continued on, they probably would have solved some of the problems. Am I going to do it? No. I'm not going to follow that particular course. I've got other things to do. So solid oxide, good technology, has promise, can be engineered, is cheap, is reliable, is long-lived, and uses materials that are relatively plentiful. Now, solid oxide fuel cells. The solid oxide fuel cells come in two varieties. One variety is called tubular, and the other one is called planar. The difference is one is made of tubes, hence the name tubular, and one is flat, hence the name planar. These were solid oxide fuel cells were sort of the Cinderella of the fuel cell world, and one of the real problems with solid oxide is they're ceramic based. And now, as you know, ceramic is inert, it doesn't move, you can heat it up, it doesn't change shape, doesn't change size. Unfortunately, you have to put other materials on as catalytic materials, etc., such as zirconium. Now, zirconium is really quite a good metal, but applying it to ceramics is difficult, but it can be done, and it is done quite often. In fact, most solid oxide fuel cells work with zirconium put onto a ceramic base. Now, the problem is, of course, is you have variations in temperature. So it's best that once you start a solid oxide fuel cell, you don't stop it. Because once you start stopping and starting, what happens is you get delamination of the zirconium on the ceramic base. So that's a real problem. Other than that, it's very efficient, 70 to 80% efficiency. It runs at high temperature, so it can be self-reforming. So it's a very interesting and useful technology. The problem is that you can only make relatively small sizes of it. Now, how that's going to be reflected in the future, one doesn't know. I have colleagues who have been working on this problem for some time, and they're not stupid. They will eventually crack the problem, and then the cost of solid oxide fuel cells will descend rapidly. Whether it descends as rapidly as other types of fuel cells is a big question, because the actual deposition of zirconium on ceramics is not a simple process. It's quite complex, and it's not always terribly efficient. So of the two types, the tubular and the planar, the tubular is the older type and is made to this day, particularly in California, Korea, and places like that, and is used well. Its input gases are the same as every other fuel cell: hydrogen and air or oxygen, and as I said, the efficiency is very high. Now, planar is a different kettle of fish altogether. It is flat. It has particular problems in sealant on the between the electrodes, but that's not just in solid oxide fuel cells. That runs across all fuel cells basically, but it's particular problem in high temperature fuel cells. So sealant becomes a particular problem, and what happens is that when you have a problem like that, you tend to want to seal the thing forever because it's easier, and then that becomes a problem in maintenance and replacement. So those are the basic high temperature fuel cells. As said before, they're good fuel cells. Even the phosacid fuel cells are good. They're good for transportation in particular. The original fuel cell bus was made in Georgetown in the state in Washington, in the capital of Washington of the United States. And it, as far as I know, Georgetown University is still running it, or running it as a demonstrator. It's a pretty good piece of kit. The phosacid fuel cell, I don't know of any that are particularly running, but they did try it in naval applications and found it wanting, but it is potentially a very good fuel cell. Finally, solid oxide fuel cells. Yes, I'm a sort of a fan. I don't think that while we may see it as stationary applications, I don't think transport applications are appropriate for it because of the need to stop-start. So there you have it for this particular bit. The next bit, I'm going to go on to the really difficult part, which is the low temperature fuel cells, where there is some real disagreement as to their use. Until then, thank you very much.